Shall we start? Shall we wait? 8 o'clock, 8:01. So we are going to start a new chapter. The last chapter we just talked about charges, electric force, electric field, Coulomb's law, Gauss' law. Roughly, those are the keywords I can think of now. We talked about conductors, properties of conductors. So now here we are going to start energy, electric energy. So when we have a force, that force can do work. That means we can have energy associated with that force. So like gravitational force can do work, and therefore we have energy associated with that. Electric force also can do work. It's a conservative force like the gravitational force. So we can associate with this force electric potential energy. Like we have the gravitational potential energy, we can have electric potential energy. So we just call it electric energy. The chapter title is Electric Energy and Capacitance. So a capacitance here refers to how we can store electric energy, okay, in what is called a capacitor. So that capacitor will have certain capacitance to store electric energy. The contents of the chapter, here we have it, 8 subtopics or sections we call. In section 1 or topic 1, we'll introduce this electric energy. So properly it will be called electric potential energy, but sometimes we will drop the potential, we just call it electric energy. Then we also have something different but related to the energy called the electric potential. We have to understand this is energy, this is something related to the energy, but the symbol we use is V and it is potential. Sometimes probably you heard the voltage, okay, in electric circuit it is called the voltage. So electric potential and electric potential energy. We'll introduce this, okay, so we still don't know what they are, but I'm telling you the content of the chapter. Topic number 2, then we'll continue with more details about what we learned, potential and potential energy due to a point charge. Okay, when you have just a small point charge, the electric potential and potential energy associated with this point charge, we will get formulas and so on. We'll start with uniform electric field. But point charges do not give uniform electric field, but we can have uniform electric field. With that, we will introduce the potential energy and the potential. In topic number 2, we look at the electric potential and potential energy due to point charges, which are not uniform electric field. They give rise to non-uniform electric field, point charges. Number 3, then we look at potentials and charge conductors and equipotential surfaces. Equipotentials mean equal potential. That's the equipotential. So we will see that, we will visualize this potential by drawing surfaces which are having, in which we have the same potential. So that is called equipotential surfaces. Number 4, we look at applications of this energy concept that we are learning. Then how we stored energy. We store energy, electrical energy in capacitors, a device called capacitors. Number 6, we will see how when you have combination of several capacitors, how to deal with that. So combinations of capacitors in electric circuit. Then we will I'll give you the equation for energy in a capacitor. Then we will see what happened in this we saw capacitors, right, in chapter 15, two plates, one is positively charged, one negatively charged. This is called the capacitors. So that is how we store electricity in a capacitor. And we will see what happened in the gap between the plates if we put a insulating material, which is called the dielectrics. So this is the overview, the contents of this chapter. Now let's attack one by one. So we'll start with defining what potential energy is. This is a useful concept, okay, like gravitational potential energy, that is for gravitational force. So electric force is also conservative force, so we can define potential energy for electric force. It is very useful in the study of electricity. Potential energy function can be defined for this electric force. And in addition to the potential energy, we also defined something called electric potential. So now you should not confuse these two things. Potential energy is one thing, potential, we don't say energy after that, that is another thing, but they are related. We define potential in terms of the potential energy. This concept of potential is very, very crucial. I mean, relates to circuits. Probably you heard voltage, this term voltage. That's how we refer to the potential in electric circuit. The same thing, but different name there, label there. Right. So this electric force given by the Coulomb, so we can also call it Coulomb force, is a conservative force. So since it is a conservative force, like we saw for gravitational force, we can define potential energy. Similarly, it is possible to define an electric potential energy for the electric force, electric potential energy function. How? I don't know how many of you remember this. We did this in our mechanics. This is how we define the potential energy. We say the work done by any conservative force, electric force is an example of a conservative force, is equal to the negative of the change in the potential energy. So this is how we manage to define the potential energy in terms of the work done. So we can put it the other way around. We can say change in the potential energy for the electric force is equal to negative of the work done by the electric force. Okay. So this is how we define the potential energy for any conservative force, and electric force is a conservative force, so we can do that. So we will start with the simple case of a uniform electric field. We have it in the capacitor plates. So we saw that in chapter 15, when we have two plates like this, one is positively charged, the other one is negatively charged. Between these two plates, we do have an electric field which is constant in magnitude in the same direction. So we say it's a uniform field. So between the capacitor plate, we do have a uniform electric field, meaning it is the same value everywhere in the same direction uniformly everywhere in the space. So it's a uniform electric field. So now let's apply our definition of how to get the potential energy. The potential energy is the negative of the work done. So this is how we get the potential energy. So in order to do that, I need to get the work done. Let's look at the work done when we move a charge Q inside this electric field, a uniform electric field, from point A to point B. So work done, which again, if you remember, if the force is a constant, because electric field is a uniform electric field, the electric force coming from that electric field will be a constant. So it will be simply the force multiplied by the displacement while this charge is moving, let's say a distance of delta x. So that will be the displacement. So the work done will be the force multiplied by the displacement. The electric force will be if the electric field is E, it will be Q, the charge of that charge, multiplied by the electric field. So I substitute for the force by QVX. Displacement will be the final position of the charge minus the initial position of the charge. So we get this expression for the work done. So we have to get the negative of that. So you put it like here, then you put the negative sign. So this is the expression we get for the change in the potential energy as the charge is moving from point A to point B. The potential energy is equal to negative Q, the electric field E, multiplied by the displacement. So we get this equation. So I highlighted it and put it in a box like this. So now you know this is one equation that you are going to be using. Remember, this is a special equation. It's not always correct for the change in the potential energy of an electric field due to an electric field. This applies to a uniform electric field. Okay, when the electric field is constant, then I can say the change in the potential energy when a charged particle Q moves from A to B, when it is at point A, it will have a certain energy. When it comes to the point B, it will have another electric potential energy. The change in the electric potential energy is equal to negative charge of that particle multiplied by the electric field multiplied by the displacement. So, and you know it's an energy, therefore it is going to have the unit, the SI unit will be joule. We have seen the energy before, it is not the first time, and you know energy is force multiplied by the displacement, so it will be Newton meter, but we have an official name for Newton meter, which is joule. So electric potential energy is also in joule. So this is equation number 1, you come in this chapter. When we have a uniform electric field, and if you move a charge Q from point A to point B, the change in the potential energy that that particle experiences as it moves from A to B is given by this equation. You have to put the signs correctly, okay? So if the electric field is in the x direction, it will be positive. If it is the negative x direction, it will be negative. And Q must also be substituted with the sign. Not because it's a scalar, but it has sign. Positive charge will have a positive sign. Negative charge will have a negative sign. Right. Then comes the definition of potential difference, potential, electric potential. So we define potential energy. The symbol we use for potential energy is PE. How did we define? We say the change in the potential energy is the negative of the work done by that force. Okay, we associate the potential energy to a force. So that is potential energy. Now comes another concept, which is not potential energy, but potential. We stop there. We don't say potential energy. So the potential, the symbol we use for potential is V, as in voltage, okay? So it is the same thing, but in circuit theory, it becomes voltage. So potential difference can be thought of as the voltage difference. So V is the symbol we use for potential. PE is the notation we use for potential energy. The potential is the V is related to the potential energy through this equation. So what it tells you is the electric potential difference, delta V, you know, delta means difference, is defined as the change in the potential energy divided by the size of the charge. So potential difference or change in the potential is equal to change in the potential energy divided by the size of the charge. So delta mean final minus initial. Again, I have to stress this. Potential difference, that means delta V, is not the same as potential energy or the change in the potential energy. So this is how they are relating. Delta V is equal to delta PE divided by the size of the charge. Okay, so you can say the relationship is somewhat similar to the relation between electric field and the electric force. Electric field is the force per unit charge. In the same way, potential difference is the potential energy difference divided by the charge or per unit charge. We can now, this, you said this is here, right? I can bring it up here and I can put it like in this manner. Another way to relate the energy and the potential difference like this. You can say potential energy change is equal to charge multiplied by the difference in potential or potential difference. This is potential energy change is equal to Q multiplied by the potential difference, change in the potential. Both of them, potential energy is a scalar and potential is also scalar. They are both scalar, but they can have sign. Okay, potential energy can be negative and potential can also be negative, both negative and positive, but it doesn't indicate any direction. It's a scalar. Energy can be negative and the potential can also be negative. They are scalar quantities. What about the units? So it's clear now, this is joule and this is coulomb. Therefore, the unit for potential will be joule per coulomb. Unit for potential is energy divided by charge. So it will be joule per coulomb. But as always, happens, not most of the time happens, we give instead of calling it joule per coulomb, we call it voltage, volt. Joule per coulomb, the official name for joule per coulomb is volt. So the potential, the unit for potential is volt. Potential or potential difference is volt. The symbol is V. The symbol for potential is also V. The unit is also V. Now again, we can get the special case when the electric field is uniform, because we can say that delta V is equal to Q, change in the potential energy divided by Q, and we derived an equation for change in the potential energy in the case of uniform electric field to be QE delta X, an electric field in the X direction, divide by Q, Q cancel with Q, so we get this special result for the potential difference is equal to minus EX delta X. Again, remember, this is a special result when the electric field is uniform. The potential difference between 2 points A and B will be EX delta X. Delta X is the distance from A to B, or the displacement rather, not distance. So now if we take this equation, we can see that this has the unit of V, the unit for potential is V, and E has the unit Newton per Coulomb, and delta x is meter. So if I combine this and I bring this meter to this side, so you can see the Newton per Coulomb, which is the unit for electric field. So electric field unit is Newton per Coulomb, and Newton per Coulomb is identical to volt per meter. So in other words, I can say electric field can be the unit for electric field. The SI unit for electric field is also can be given as volt per meter. It is Newton per Coulomb, that's the definition, force per unit charge. But now we are relating the potential difference and the electric field by this equation. So that tells us an alternative unit for electric field is volt per meter, identical to Newton per Coulomb. Electric field, electric potential is characteristic of the field only. It doesn't depend on the test charge you bring in. It is like when you talk about the force, we have a charge, you have to bring in another charge, so interaction between these two charges, or the interaction between the second charge on the electric field from the first charge. So that is electric force. But the electric field, when you talk about the electric field, it depends only just one charge. Okay, so it does not depend on the test charge you bring in. In the same way, when you talk about the electric potential energy, electric energy, we need to talk about the interaction of one charge with an existing electric field. But for the potential, it's just the potential due to a single charge or some electric field coming from some source. It is independent of any test charge that may be placed in the field. In a same relationship, what you have between the force and electric field, we have the same thing between electric potential energy and the electric potential. Electric potential energy, on the other hand, is a characteristic of the charge and the field system. So the interaction between the field and the charge placed in the field. So this is where we stopped, right? We talked about potential energy compared to potential. Two different things. Potential energy is energy. Potential is energy per unit charge. They're not the same, they are related. All right, let's move to the next slide. So, yeah. Thursday. It's already. Yeah, in the syllabus also I send a notification. Check the announcement, it's there. Okay. Check the calendar, it is there in the calendar as well, in so many places. I sent a notification. There was a short notification. I made changes to it is also in the Moodle page, you can see there. Next Thursday, I believe it's 4 p.m. Can someone verify that? Check. All right, let me continue. So if we take a positive charge and we release it in an electric field, it will move from point A to point B, where point A has a higher potential and point B has a lower potential. In other words, a positive charge will move from high potential to lower potential. Okay, positive charge will move from high potential to lower potential. So if I take a capacitor plate, between the capacitor plate, from the positive, negative, and electric field will be like this. So at the positive plate, we will have high potential, and the negative plate, you will have a lower potential. Like a battery, battery, the positive end is at a higher potential, and the negative end is at a lower potential. So if you release a positive charge, it will move to the negative plate. The negative plate has a lower potential, the positive plate has a higher potential. So you can kind of remember this. A positive charge will accelerate by itself. It will move towards, from the high potential, it will go to the lower potential. So you see the reason very clearly. So positive charge, it will be attracted to the negative plate. Negative plate is at a lower potential and the positive plate is at a higher potential. On the other hand, if you take a negative charge and release it from rest, what do you think will happen? Suppose I release it in the middle, a negative charge, say like an electron. It will go to the positive plate. That means it's moving from the lower potential to higher potential by itself. Positive charge will go from the high potential to the lower potential. Negative charge will move from lower potential to higher potential. So what happens is, if you want to move the other way around, so if you want to force this electron, which is a negative charge, to go to the negative plate or to the lower potential, then we have to do work because it is going to be repelled by the negative plate. So one has to do work to make it move to the lower potential. Work must be done on a negative charge just to make them go in the direction of lower electric potential. For the positive charge, the other way around. If you want to make the positive charge go to the higher potential, we need to do a positive work. Must be done on the positive charge to bring it to make it move to the higher potential. Now we come to get an expression for a non-uniform electric field. From point charge, if you have a point charge, the electric field is not the same. As you go away from this point charge, the electric field decreases. So it is not a uniform electric field. And by taking the zero potential at infinity, because electric field at infinity is going to be zero. So we take the potential to be zero at infinity. Then using some calculus, because the work done by a charge when it is moving, it is a non-uniform electric field. We need integration and so on because it's not a constant electric field. We don't have to worry about how you get the result because integration is not part of the syllabus. We just give you the expression for the potential, not even delta V, V itself, the absolute value, because we are referencing the potential at infinity to be zero. So we have a reference point which is fixed. And the potential at a distance of r away from the point charge, say let me take this point P, which is at r distance, is given by this equation. The potential created by a charge Q at any distance r from the charge can be shown. You don't need to worry how it is shown, okay, because it involves some calculus, integration, and from the definition of the potential energy and using methods of calculus, we arrive at this equation. So another equation for you to know, okay. Memorize if possible, but don't worry if you forget it because it will be in the formula sheet. So the potential due to a point charge at a distance of r is given by this equation, where k is the constant that comes in the Coulomb's law. Q is the charge of the point charge with the sign. If it is positive, you have to put it as positive. If the charge is negative, you have to put it as negative. So this gives the potential, not potential energy. V is for potential for a point charge at the distance of r. So another equation, a formula to remember. So, you know that electric field, on the other hand, for a point charge is given by this equation. And the potential is given by this equation. What's the difference? Electric field is 1 over r squared. Electric potential is 1 over r to the power 1. That's the difference. So if you draw a graph of both electric field and the potential as a function of R. You get two lines, one for electric field, which is the brown line, and one line for electric potential, which is the blue line. So because this is 1 over R dependence, it drops little less rapidly, but the orange line or the brown line, which is for the electric field, it drops rapidly, faster, because 1 over R squared. And you see the unit for electric field is given as volt per meter. Earlier you saw it is joule per coulomb, but now I have shown you they are identical. Electric field can be thought of as having the unit volt per meter or joule per coulomb. They are the same. Right. Now, so electric potential obey the principle of superposition. It's like, say, suppose you have a charge Q1, and due to this charge Q1 in the space, at this point, you will have the potential due to this charge 1 as V1. You can have another charge, say Q2, and due to this charge 2, at the same point, it will create a potential, say V2. Then you can say, I can apply the principle of superposition. If someone asks you what is the total potential, the net potential at this point, you simply add them. You take the potential from Q1 and then the potential from Q2. Both of them will contribute to the electric potential at that point. You simply add them. So superposition principle applies. The total electric potential at some point P due to several point charges is the algebraic. Okay, I have to stress this point because Q1 may be negative. So V1 will be negative. Q2 may be positive, then V2 will be positive. So you have to keep the sign. Okay, you have to consider they have sign and you have to take the algebraic sum. When you say algebraic sign, you should not ignore the sign. Positive, you have to put positive. When it is negative, you have to put the negative. Yeah, but they are not vectors. They are not vectors, but they can have sign. So it's not vector addition because potential is not a vector. So it's a normal algebraic. Okay, I have to stress the algebraic, but remember to put the correct sign. They are not directions. It is just scalar quantity with sign. Dipole. We saw dipole and we should know what dipole is. Anyone remember what an electric dipole is? I told you in the last class, chapter 15. It's a certain configuration of charge. Very good. Okay, so when you have two point charges, same magnitude, opposite sign, it has a special name. Electric dipole. Sometimes you drop the electric, you just say dipole. Okay. So suppose you have a charge here, which is a positive charge, and another charge here, which is a negative charge. Same magnitude, opposite sign. Then in a three-dimensional space, I can get the, using the superposition principle, what is the potential? So the potential near to this guy, it will be very high. The potential will be positive infinite. Near the negative guy, it will be negative infinity. So in between, they will have, say, at the middle, between the two, the potential will be 0 because one is the same magnitude, same distance away. So this will contribute to some positive value. This will contribute a negative value of the same magnitude. They will cancel each other. The potential in the middle will be 0. So if you put a three-dimensional plot, this is how it will look. So it's an example of a superposition. You simply add with the sign. Right. Now we jump back to energy. We were looking at the potential. Now, what about the electric potential energy of a charge interacting with the field due to another charge? So let's say initially we have a charge Q1 in this place. So from this charge Q1 at the point P, the potential due to this charge Q1 will be given by our standard equation K Q1 over R. So let's say at a position R, it will be K Q1 over R. And there is another charge which is kept at infinity. Infinity from point P, it is infinite distance away. So it will have no potential at that point. Now, if I bring that charge from infinity to that point, the work done during that process without accelerating, because you don't need any other energy except to change its potential energy. That charge Q2, it is not here now, it is in this, it is at infinite distance away, and you bring it to the point P. The work required to bring this Q2, say, let's say that label for that is Q2, from infinity to that point without acceleration, so you don't supply energy to change its kinetic energy, so only the potential energy is changed. This work is equal to the potential energy of this 2-point charge system. So now you can say that the work done for the Q2 to bring it here will be the potential energy change, because only the potential energy is changing. So Q into delta V will be the potential energy change. This is from the definition of the potential as function of the potential energy. So the work done will be Q delta V. In other words, Q is Q2, delta V will be just V1, because initial potential is 0, final potential is V1. You bring it from infinity to that point P, so the work done will be Q2 V1. This work is equal to the potential energy of this 2-particle system. So now I can substitute for V1 by this equation KQ1R1. So we get finally the potential energy of 2-particle system shown to be equal to K Q1 Q2 over R. So another equation, okay? So what is the potential energy of 2-particle system which are kept at distance of R away? That is the equation K Q1 multiplied by Q2 divided by R, not R squared, R. So now let me write that equation again, PE here, K Q1 Q2 divided by R. This is the potential energy of a 2-point charge particle system. Q1 is one charge, the Q2 is the other charge, and the distance between them is R. K is the Coulomb constant. Now, this, when you substitute for Q1 and Q2, you have to substitute with the sign. If both of them have the same sign, positive, positive, or negative, negative, positive multiplied by positive will be positive. Negative multiplied by negative will also be positive. So if the charges have the same sign, the potential energy will be positive. Yeah, I'll come to that. Yeah, I'll come to that. Let me finish this, okay? If they have the same sign, the potential energy of the 2-particle system will be positive. Okay, next. If they have the opposite sign, if one is positive, the other one is negative. Positive multiplied by negative will be negative. So if they have the opposite sign, the potential energy will be negative. Is that what you're asking me? Okay. So, you can understand why it happened. When it is the same sign, they are going to repel each other, right? So the like charges will repel, so the potential energy when you want to bring something from far to this, you need to do work to bring it, right? You keep the Q1 here, and the Q2 is infinite distance away. You want to bring it so the distance is R, not infinity. So because as you come closer and closer, this guy doesn't want it to come. It will push away. So you need to do a positive work to bring it there. So it explains the potential energy will be positive. Suppose the other one is a opposite sign, you don't need it will come by itself. You only have to hold it, right? Otherwise, it will come by itself. The potential energy is now negative. It becomes less and less as it comes closer.
About the distance R. Why isn't it R squared?
Yeah, well, we proved it, right? You want me to go back? We proved it because we said what is the potential energy? The energy to bring the Q2 from infinity to here will be, by the definition, just a change in the potential energy. Change in the potential energy is Q delta V. Okay. The potential energy will be the energy that is needed to bring the charge Q2 from infinity to this point. And delta V is V2 minus V1. V2, the final is the V1, right? I mean, at that point, initial is 0. Because when the charge Q2 is at infinite distance away, it has a 0 potential. When it comes here, the potential change to V1. At that point, it is V1. Now, V is, now your question is, why it is R, right? Because this is the expression. But I said, I'm not going to show the derivation because it needs calculus. This is not part of your syllabus. So it is, you need integration, the R squared become 1 over R. If you have some idea of integration, differentiation, I can explain. But if you have no idea, no point in explaining it. Okay, so that's how it get 1 over R. You just need to remember the formula. No choice. Right. So we can do example question. Okay. Now, unlike chapter 15, where you have, directions, vectors, we deal with electric field, electric force, they are vectors. But energy, they are not vectors. So become a little bit simpler to do questions because we don't have to, take components and so on. It's simple algebra. So what we have here, two charges, Q1 and Q2. Q1 is placed at the origin. Q2 is placed in the x-axis at 3 meters and 0 y coordinate. One is positive, Q1 is positive, and Q2 is negative. Then the question is, at the point P, which is along the y-axis, y is equal to 4 meters, x is equal to 0 meter, what is the potential? Simple question. Okay, because it's not like, if you ask what is the electric field at point P, they are going to have direction, then we need vector algebra. But here, no vectors, simple addition, but even it's a scalar, but they can have sign, so you should not forget the sign. What is the potential at point P? So V at point P will be V1, that is the potential coming from charge Q1 plus the potential coming from charge Q2. Simple questions. Actually a simple question because we don't have to worry about direction. Potentials are scalar. And all you need to know the equation. Well, even if you forget the equation, you should know what it is about. The potential due to a point charge. And it is in the formula sheet. Sometimes you even have the description. I can't remember whether you can check it in the formula sheet. Is K Q over R. So for 1, it will be Q1 and R1. Plus, for the charge Q2, it will be K Q2 over R2. Of course, you need to know what R means. R means the distance from the charge, that particular charge, to where you want to get the potential. And this is a matter of substitution. Huh? No, not radius. The distance from the charge to where you want to get the potential. So for Q1, I want the potential at point P. So the distance from Q1 to the point. It's not radius. The distance from the charge to where you want to get the potential. So that will be R1. R2 will be the distance from Q2 to where you want to get the. So that will be, let me use another color so I can refer to them by color. So the red line will be R2 and the blue line will be R1. It's a matter. Maybe it is done in the next slide. So let me go to the next slide. Yeah. You get the V1. K is the constant. Q1, this is very important, okay? Q1 is given somewhere, right? Where? It's all positive. No, Q1 is positive. So you put plus. You don't have to put the plus, right? If it is plus, you can just leave it. It is understood it is plus. And R1 is this. So you know if it is 0, 4, this distance will be 4. And you just take your calculator, get the answer, and you know if you put everything in a SI unit, the answer for the potential will be in volt. Which is
why did you put 10 by power of -6?
Where did I put? Okay, good you asked me. You know, Coulomb is the SI unit. So microcoulomb is not SI unit. So you have to convert the microcoulomb to coulomb. So it is -6. Right, got it. Now you calculate the V2. So it will be KQ2 over R2. So R2 will be, these are R is a magnitude, okay? R is magnitude, that doesn't have sign. But Q has a sign, not because it's a vector, it is not a vector, but Q can be a positive charge or negative charge. So you should put with the correct sign. Since Q2 is a negative charge, although the question it says it's a charge is this, that's the magnitude, okay? But here you can see it's a negative charge, so you should put negative. So you got the V2. And total potential, superposition principle, you have to add them. But, you know, you should not drop the sign. You have to add with the sign. So you get this answer. Then part B, how much work is required to bring the third point charge, 4 microcoulomb, Q3. I want to bring Q3, which is an infinite distance away. So it will have no effect at this, is 0 potential. You're going to bring it from infinity to that point. At infinity, it has a 0 potential. And you have to bring it to this point, which has this much of potential due to these two charges. So that will make the work done is the energy of the system, because you are forcing another charge which is at infinite distance away and bring it there. How much work is required to bring the third point? So he's asking, when you just the energy due to that only, to bring that charge Q3 from infinity to that point simply will be, because you are not changing its kinetic energy, so all we need is the change in the potential energy as we bring it from infinity to this place. So it will be Q3, that is the charge that is being brought in, multiplied by, because change the potential energy, by the definition it will be equal to Q into delta V. So delta means final potential. Final potential is the potential because brought to this point finally, potential at the point P minus the potential at infinite distance away, which is 0. Substitute for Q3, again, you have to put with the sign. Here he doesn't tell me whether it is positive or negative. So since there is nothing mentioned, so you have to assume it is positive. And this is the potential when it is at the point P, and this is the potential when it was initially infinite distance away, and you get this answer for part B. All right, so now we did the question on potential of 3 charges and work done and so on. We go to a new topic, potentials and charge conductor. Let's say we have a conductor which is charged, meaning it is not neutral. It has either excess positive charges or excess negative charges. And we want to talk about the potential in this charged conductor. We know about some properties of conductor which you learned in chapter 15. And one of the property is on a conductor, electric field, the excess charges will, suppose the excess positively accessed. So excess charge will come to the surface if there are any positive excess charge. Let me assume it is positively charged. It will come to the surface. And the electric field on the surface, inside it is 0. These are properties of conductor which he kind of proved, which you have to remember. For a conductor which is in electrostatic equilibrium, isolated from everything else, so nothing is moving, so it's electrostatic equilibrium. Excess charges will come to the surface, and the electric field will be perpendicular to the surface at every point along the surface. Here the perpendicular is like that, here the perpendicular is like that, and so on. It will be perpendicular to the surface, since it's positive to be outward. And you know the work done is the change in the negative of the change in the potential energy. For potential energy, I can write Q into delta V. And if we have 2 points which are at the same potential, meaning potential at A is equal to the potential at B, that delta V will be 0. That will say that the W will be 0. So if you have 2 points which are of the same potential, you don't need any work. The net work will be 0 to bring a charge from point A to point B if they both have the same potential. So just remember this. When you have 2 points, A and B, and if the potential at A is equal to potential at B, then you don't need work to network. Okay. Maybe they may be doing sometime positive work, sometime you'll be doing negative work. The network will be 0 when you bring the charge from A to B. Now, knowing this, we can prove this, what I have emphasized here in bold. All points on the surface of a charged conductor in electrostatic equilibrium are at the same potential. If you take a conductor like this, if you take 2 points on the surface of the conductor A and B, these 2 points are at the same potential. Any 2 points on the surface of the conductor is at the same potential. And the electric potential is constant everywhere inside the conductor and equal to the same value on the surface. Not the electric field, I'm talking about the potential. So every point will have the same potential, and the potential inside that conductor will have the same potential as the potential on the surface of this conductor. So if we have a charged conductor which is in electrostatic equilibrium, that conductor has a constant potential. Not only on the surface, it will be equal to the potential inside the surface as well. Now, don't confuse the potential with the electric field. Electric field will be zero, but the electric potential will be the same electric potential that is on the surface. We can now prove it. This is where we are trying to prove it. Let's say the conductor has an excess of positive charges like that. So we said the electric field will be perpendicular to the surface like this. And let's say you want to take a charge from point A and bring it to point B. So you want to move the charge at point A and move it to point B. What will be the work done? A is on the surface, B is also on the surface of this conductor. And I'm going to move the charge at point A along this path, along the surface to the point B. What will be the work done? Why? Work done, force multiplied by delta x, right? Is actually the scalar product between the force and this. Force will be, because electric field is like this, the direction of the force will be perpendicular everywhere. Force will be if it is positive charge, okay, it will be in the same direction as the electric field. The force will be perpendicular to the surface. As the charge is moving from A to B, the force will be perpendicular to the surface. And the delta x, every time, if you imagine a small delta x, it will be parallel to this will be parallel to the surface. And this will be perpendicular to the surface. Force will be perpendicular to the surface, and the delta x will be parallel to the surface. What is the angle between F and delta x? Now, what is the angle? 90. Cosine 90 is 0. So, scalar product means we have a cosine, right? It's F delta x cosine theta. Theta is 90 all the time. Cosine 90 is 0. That will make the work done as you move a charge on the surface from point A to B. There will be no work done. Right, we conclude that the potential, because of the points, if the charge is moved from A to B, no work is done because E is perpendicular to the displacement. No work is done because E is perpendicular to the displacement. This tells you the potential is constant everywhere on the surface of the conductor because, initially I told in this slide, okay, if there's no work done, that means the potential is the same from A to B. So I have just proved there's no work done. Then we can say, because when you move from A to B, there's no work done, we can conclude potential at A is equal to potential at B. Right? We told you earlier, when potential at A is equal to potential at B, the work done is 0. Now you prove the work done is 0, therefore the potential at A is equal to potential at B. And then we can continue to say, because if you take any point inside, that point can be arbitrarily brought closer and closer to the surface. That means even the points inside the conductor will also be at the same potential as any point on the surface of the conductor. So we conclude that the potential everywhere inside the conductor is constant and equal to its value at the surface. Right. So I will finish with this slide. Okay. So energy unit is joule, right? And what is the unit of energy? We did this in the mechanics in the last semester. Energy unit is joule. Then we said joule is very small unit. When you consume electricity, we consume millions of joule in few seconds, for 1 minute. So electricity board, if you want to charge you, 1 joule is a small unit. So we need to define a big unit, which is a kilowatt hour. I don't know how many of you remember that, which we did in chapter 5 or something, okay, in the last semester. So compared to what we consume in a house for these light bulbs, the fan, the heater, AC, 1 joule is negligible. So you need to talk about million joule, which is kilowatt hour is 3.6 million joule. So we make that as our standard unit, kilowatt hour. But when you go to atomic physics, like the binding energy of the electron and so on, joule is a very big unit. So in the other end, when you go to atomic physics, when you talk about the the binding energy of an electron, we need a small unit, electron volt. So it is, although the name is electron volt, it is not volt, it is not potential, it's actually potential energy. There's a little bit confusion, but we can't help it. So electron volt is a very small joule. 1.6 into the minus 19 joule, very small. You know, we already complain in joule is very small. So when you consume energy, we consume, you know, in a few seconds, we can consume millions of joule. So we need a big unit. Now in the other end, when you go to atomic physics, the binding energy of an electron, for example, very, very small. We need a small unit. The small unit is this. 1.6 10 to the minus 19 joule, we call it 1 electron volt. Because it's to do with the electron, that's why the word electron coming in. The electron volt is defined as the kinetic energy that an electron gains when accelerated through a potential difference of 1 volt. So you know the potential energy change is Q delta V. If we make this 1 volt, okay, and this is the charge of an electron, which is 1.6 into the minus 19. So this much of energy is called 1 electron volt. You know, it's one. That's where this 1.6 into the minus 19 is coming. Electrons in normal atoms have energy of tens of electron volt. I think the hydrogen atom, the binding energy of the electron in ground state is like 13 electron volt or something. I don't remember now, something like that. When you excite it, it can go to an energy of thousands of electron volt, 1 mega, 1000 kilo electron volt. Yeah. But in the case of gamma rays, okay, can have energies of millions of electron volt. Okay.